Have you ever noticed how quickly clothes dry on a breezy day compared to a still, humid one? Or felt that refreshing coolness from a fan, even if the air itself isn't colder? These everyday experiences offer a hint about a fundamental process in hydrology and meteorology. Air velocity significantly increases the rate of surface evaporation. This happens because moving air efficiently sweeps away the water vapor that has just evaporated from the surface, constantly exposing the liquid water to drier air. This continuous removal of humid air prevents the air immediately above the surface from becoming saturated, thereby maintaining a strong driving force for more water molecules to escape. To understand why, let us consider the thin layer of air directly above a water surface, known as the boundary layer. As water molecules evaporate, this boundary layer becomes saturated with water vapor. Evaporation is driven by a vapor pressure gradient, meaning water moves from an area of higher vapor pressure, like the saturated surface, to an area of lower vapor pressure, like the drier air above. If the air above the surface remains still, the boundary layer quickly saturates, reducing the vapor pressure gradient and slowing evaporation to crawl. However, when air moves, especially at higher velocities, it constantly disrupts and removes this saturated boundary layer. This brings fresh, drier air with a lower vapor pressure into contact with the water surface, continuously re-establishing a steep vapor pressure gradient and accelerating the rate of evaporation. Faster air also creates more turbulent eddies, which are small, chaotic air currents that enhance mixing and efficiently transport water vapor away from the surface. This principle is crucial in many practical applications. For instance, in industrial drying processes, fans or blowers are used to increase air velocity over wet materials, drastically speeding up water removal. Similarly, in arid regions, high winds contribute to significant water loss from open water bodies such as reservoirs and lakes, a key consideration for water resource management. Understanding this mechanism allows engineers and hydrologists to predict and manage water loss more effectively. The efficiency of this vapor removal is often quantified using terms like aerodynamic resistance, which is inversely related to the ease with which water vapor can move from the surface into the atmosphere. A lower aerodynamic resistance, typically associated with higher wind speeds, means faster evaporation. We also consider factors like the fetch, which is the distance wind travels over an evaporating surface. A longer fetch allows more interaction between the wind and the surface, influencing the development of the boundary layer and the total evaporative flux. Ultimately, recognizing how air velocity modifies surface evaporation is vital for comprehending global water cycles, from predicting rainfall patterns to managing agricultural irrigation. It underscores the dynamic interplay between atmospheric conditions and hydrological processes, providing a deeper understanding of how water moves and transforms across our planet.
If you love learning about water, like, subscribe, and keep exploring with us.